we put everything at a sort of a standard nearby distance of the absolute magnitude is the apparent magnitude of a star at a distance of what? 10 parsec. Need to know probably what the absolute magnitude of the sun. Absolute magnitude is about 4.5. That's how bright the sun would be. In other words, it would be a pretty, if it were 10 parsecs away, solar type star, pretty dim. You know, it's a naked eye star, but not terribly impressive. The Milky Way is going to be somewhere here around minus 21. Okay, it depends on which wavelength we're measuring. Blue, visual, red, go to longer wavelengths here, where the galaxies get relatively brighter compared to A stars. This is the logarithm of the velocity width, usually measured with 21 centimeter profile of H1 from a radio telescope. Since there's a flat rotation curve and most of the hydrogen is at this maximum velocity, this is giving you the maximum rotation velocity. Well, twice the maximum rotation velocity because there's one side of the galaxy compared to the other side of the galaxy in kilometers per second. This has been corrected. We want the intrinsic speed that the stars and gas are going around, not the apparent speed. So we had to correct it for the inclination angle sine of I, right? If you were viewing by accident a spiral galaxy disk, a very flat round disk face on, you would measure 0 Doppler shifts. But these measurements are corrected if you were measuring it exactly edge on. I don't want to study face on spiral galaxies for this work because they're kind of too hard to correct it all the way to know exactly what the inclination correction should be. All right, and here is the embarrassingly good correlation that Tully-Fisher came up with. They were originally using blue data. Over time, though, this original graph on the upper left here has been discarded in favor of longer wavelengths, where the correlation between, say, the red light or even the infrared light of the stars in a galaxy is much tighter correlated with how fast it's rotating. And that's determined by the gravitational potential of the dark matter. So we've got the visible matter of starlight on the vertical axis correlating beautifully with the dark matter that causes the gravity, that causes the rotation. Blue light in particular is very badly absorbed and scattered by interstellar dust, and we don't know very accurately how to correct for that. At long wavelengths, not much to correct for, and you've seen this in pictures of the Milky Way. You can see right through everything. That is the number one best reason why the long wavelengths are better. Why would there be more scatter if you're looking at the blue light? The blue light of the galaxy can vary enormously depending on whether it's just recently formed a lot of upper main sequence stars. See, the mass might be the same. The mass is mostly in the old stars, but the appearance of it in the blue and the ultraviolet can vary enormously, just producing a lot of scatter in this diagram. But if you're looking at the long wavelengths, the red light, it's a composite stellar population. You're primarily measuring the old stars, which really traces the mass of the star. These galaxies have extra accurate distances. That's why we know exactly where to place them on the vertical axis here, because they were from the Hubble Space Telescope Key project. Cepheid variable stars that obey the period luminosity law so that you know how far away these individual galaxies are. Elliptical galaxies generally, but I'm going to even be a little more general and say spheroidal, non-disk-like distributions of stars. What else might be included here? Bulges of spiral galaxies, which are clearly not a disk. Took a photograph. They measured what the major axis of the galaxy is down to a certain brightness level, the minor axis, and so 1 minus the minor axis over the major axis, basically the ellipticity, multiply that by 10. And we get the number, this is an E4. So that means 1 minus B over A is 0.4. And this galaxy down here is as flattened as they get. And you'll notice, of course, it's not nearly as flattened as an edge-on spiral galaxy. B over A is 0.3 here. That's an E7. You don't see too many of them. If you want to call that an E7, go ahead and call it an E7. Many other people might call that a armless spiral galaxy. Kind of looks almost like a disk. That's an S0. This has a very smooth brightness profile, some nice mathematical law, a simple empirical formula that describes how the brightness drops off as a function of radius. Brightness measured as a magnitude per square arc second, typical elliptical galaxy. Way back in the 60s, I guess, had a bunch of different kind of graph paper. So let's just stretch or distort the horizontal axis. Let's pay attention to the right-hand side of the graph because that's the success. If I plot the 1/4 power of r here, I don't know why. Purely empirically, these elliptical galaxies typically will give you a straight line relation. And I like a straight line relation because that takes only two parameters, the central surface brightness and then the characteristic scale length. This is called the de Vaucouleurs r to the 1/4 law for spheroids or for elliptical galaxies. Define an effective radius. This is clever. What's the effective radius? The effective radius is how far you have to go out on the straight line until you hit a circle, you know, in the galaxy that encloses half of the total light of the galaxy, which would mean you'd have to actually do a slightly messy integral all the way out from r equals 0 to infinity of this law. Well, de Vaucouleurs did it. I'm not going to make you do it. If you scale everything to the effective radius, then this is the total luminosity of the galaxy. This should look pretty familiar. And by picking the correct number, this magic 3.33, that's how he defines the effective radius to include half the light. He did not define as the surface brightness at the center at r equals 0. Remember, that was Freeman's law. Instead, he defined it at the much more useful and practical isophote. This is the surface brightness at r equals r effective. You can see when r equals r effective, this is 1. This is 1 minus 1 is 0 here, so we have 10 to the 0, which is 1. This is the surface brightness at r equals r effective. I'll let you in on a dirty little secret right now. Nobody ever measures the central surface brightness of elliptical galaxies. Certainly, it was impossible for de Vaucouleurs to do it because this straight line isn't going to work in the center of the galaxy. And he knew it wouldn't work. And he had an excuse why he could ignore everything inside a few arc seconds. Astronomical seeing is doing ground-based observations. Everything in the inside here is just smeared out into a constant surface brightness inside the seeing disk. So he didn't know what was going on in here. And his formula, it gives a ridiculous prediction. It goes up to a very high surface brightness, which is never observed, but de Vaucouleurs said, that's okay. That's just inside the seeing disk. So there's the formula written with not powers of 10, but powers of E, because, you know, some mathematicians like E. So then I had to take the 3.3 and multiply it times 2.5. Didn't I? Because the Greeks set up magnitudes to be 2.5 times the law. And look what actually happens to the surface brightness as you go from the effective radius to r equals 0. Gets pretty pathological. Formula says that the brightness going in there would be 2,000 times brighter than at IFX. Converted this into magnitudes here. Mu is magnitudes per square arc second. Look at this law that we had here. Like, how did de Vaucouleurs decide it was 1/4? It could have been like anything. It could have been 1 over n. And in fact, Sirsic, another clever guy, n doesn't have to be 4, although that's a very good description of your typical elliptical galaxy. Maybe n could be anything. I mean, it could be larger than 4. It could be less than 4. Define things the same way de Vaucouleurs does. Here's the R effective, the radius which encloses half of the light of the total galaxy. Little b constant is going to depend on what n was. Sirsic has generalized this. One Sirsic law now can actually have a 2-parameter fit. There's your size and your brightness scaling. And we can fit elliptical galaxies and spiral disks with just one law. The main difference being that we want n is around 1 for a spiral disk. That's what we saw last week. And we want n is around 4 for an elliptical. Boiled everything down to 2 parameters for an elliptical galaxy. Basically, its characteristic half light size that can close the half of the light, how big it is, and then the characteristic surface brightness of it. Freeman did this, you know, with the spiral galaxies, and he looked for some additional law, some additional pattern. A lot of my spiral galaxies tend to have a fairly constant central surface brightness. I wonder if there's some kind of law for the surface brightnesses of elliptical galaxies. The larger the galaxy is, the lower, the fainter the effective surface brightness, or the central surface brightness of the galaxy is. But you can already see from this diagram that you could not predict the effective surface brightness of a galaxy in magnitudes. This is a little bit confusing here. This is in visual magnitudes per square arc second, but it's called B, that's not blue, that's brightness at the effective radius, measured in the visual band. Quite a bit of scatter in this, so you could not predict one parameter just by knowing the other parameter. You plot the luminosity of the elliptical, the absolute magnitude of the elliptical, from the faint ones down here to the bright ones, brighter than the Milky Way, much more luminous, more massive than the Milky Way on the right. And you see that generally the effective surface brightness of the big galaxies goes down, but they make up for it by being much, much bigger. So they are brighter. But man, wouldn't you say this is real scatter? There must be something else going on here. Let's bring in dynamics or kinematics. Let's measure the motion. This is a big step forward because it's not that easy to do. We want to measure the velocities, how fast things are moving. In an elliptical galaxy, they generally don't have enough gas in them, very little at all, to measure. And they're generally not simply rotating flat disks at all. So instead, we have to make a much more complicated, painful measurement of this thing called sigma, the random velocity dispersion, consciously named after the sigma of a Gaussian. Right? If a Gaussian shows you the velocities of all the individual stars in this galaxy, there'll be a peak at the average velocity of the galaxy, and then sigma tells you how wide is the spread of velocities of stars in the galaxy. Orbits of stars in most elliptical galaxies are dominated not by rotation, but by random velocities in all different directions. And as you might expect, the larger the galaxy, the more stars in the elliptical galaxy, the more gravity, the more acceleration, the larger are the random orbital motion, the larger sigma. Just inspired at the beginning of this lecture by the wonderful Tully-Fisher correlation, which shows that the light of stars in a spiral disk galaxy increases as what? The fourth power of the rotational velocity. This comes from the virial theorem. Gravitational potential energy is -2 times the kinetic energy. Just like that previous graph here, there's kind of a lot of scatter here. Got a lot of scatter there, got a lot of scatter here. You need to combine the information from this diagram, which has a lot of scatter, with the dynamical information from this diagram, which has a lot of scatter, and then you can explain, quote, everything. This is just measured in the center of the galaxy. Central velocity dispersion indicates that you don't need very much dark matter in the centers of elliptical galaxies, which is similar to what we found in spiral disks as well. Why do I say that? Because the mass to light ratio measured in units of the sun, I'm going to say it's really about 5 to 10. Turns out that they have the same dark matter halos exactly we see around spiral galaxies, just more difficult to study them. This is the spread of the velocities, but each of the individual stars is seemingly going on a fairly random orbit, a little bit like the velocities of molecules in this room. That also could be described by a Maxwell-Boltzmann distribution with a sort of a characteristic speed in each of 3 dimensions. In the case of a room, I think they're moving, if they're oxygen molecules, they're moving at, what is it, about 1 kilometer per second. The stars in a typical elliptical galaxy have these random velocity spread of about 200 kilometers a second. If that reminds you of gas particles, a certain temperature, you'd be right. Some interesting differences, but it's very similar to the random motions of gas particles. I just drew a slope 4. That's the slope you might have expected if the virial theorem holds. Combining all these things together, you can predict the effective size, that's the half-light radius, of an elliptical galaxy. Quite accurate. Surface brightness goes up, the size goes down, or vice versa. So we already knew this, and we already knew from the last graph there's a positive correlation. The bigger galaxies have larger velocity dispersions. What we didn't know is exactly what these exponents would be. I don't care if you remember what these exponents are. I can't remember. You can predict almost exactly what the effective size of the galaxy is. So-called fundamental plane. It's not a fundamental line. Tully-Fisher was nice. I was comfortable with that. That was a straight line, and all the spiral galaxy disks was right on the line. With elliptical galaxies, you measure these three things, plot them in a three-dimensional space, R effective, I effective, velocity dispersion. You don't find everything falling on a line. You find everything falling on a plane. Again, it must be something connecting the luminous baryonic matter, protons, neutrons, electrons that we see, the star. With the dark matter, when you plot this fundamental plane, this magic combination of velocity dispersion and surface brightness of the galaxy, in this combination, you find that you can predict the size of the galaxy amazingly accurate. All of this generalization that I applied about the fundamental plane, I think that the bulges of a lot of spiral galaxies are included on here. Is a spiral galaxy just a flat disk that we studied in the previous week, plus an elliptical galaxy added together? So there are some similarities, like all of these photometric laws, but there's some difference. When you look at an elliptical galaxy, what is the three-dimensional distribution of the star? You're looking at just a projected view because it's transparent. Non-trivial question. It was easy for the case of spiral disks. We know pretty exactly what the intrinsic shape of the disk of a spiral galaxy is. Round, pretty much circular if you could see it face on, and very flat. Here's two elliptical galaxies, different surface brightness levels. That's called an isophoto. We're getting down to much less than the brightness of the dark night sky. Isophoto contours, they look pretty much elliptical. There's B, the semi-minor axis, there's A, the semi-major axis, and you could fit an ellipse to it. The top one, it looks a little bit disky. This is the opposite. This one here has less light at the top and the bottom, but relatively more light out here at 45 degrees, plus and minus 45, plus and minus 135. It's getting a little rectangular there. There's an ellipse. But real elliptical galaxies sometimes have deviations where there's more light along the equator or less light along the equator. Some of them are round, right? And E0 has the same B and A. But of course, many ellipticals, that's the name, duh, elliptical, they look flat. But I want you to go back and look at a picture of Jupiter, and you tell me if you think that thing is round. It's not round. It's spinning very fast. It's a ball of fluid which is spinning at almost its breakup speed. Maybe that's why elliptical galaxies also look flattened. Maybe they're spinning pretty rapidly around their minor axis. What's an oblate spheroid, such as Jupiter? It has a rotational symmetry about the minor axis. It has one short axis. You start out with an ellipse, rotate the entire ellipse all the way 360 degrees around the minor axis. I get a flying saucer. That's an oblate spheroid. It has one short axis, and then it has two long axes which are identical. See if elliptical galaxies are rotating pretty rapidly, and in particular, the ones that are really elongated, E6, E7, they must be heavily rotating. There must be dominated motions are predominantly orbital rotational around the minor axis. The random velocity sigma should be relatively small if our hypothesis is correct, that it's rotation that causes the oblate spheroid shapes of elliptical galaxies. This is a great test. Didn't work too good. How elongated they are on the left is totally round. B equals A. So they look round on the sky. Remember, this is how they appear to us. You go up here to the extremely elongated ones, E6, E7, they look very elongated. Well, statistically, you would expect that the very elongated ones should have primarily rotational motion. So their VR should be larger than their sigma. They should lie along this dotted line. Some ellipticals, particularly some of these open circles, which are actually the bulges of spiral galaxies, are in fact rotating enough that they could be flattened oblate spheroids. A lot of elliptical galaxies here that are not rotating much. They might not be rotating around their minor axis at all. An oblate spheroid is a fail. But most of the big ellipticals, these are the luminous ellipticals, hardly rotating at all. So that's not why they're flat. The typical big, classic, large elliptical galaxies, the reason that they're flat is because the velocity dispersions are different in the 3 different dimensions. What you would call the temperature of the stars is different. That is so different from a gas, would not have an anisotropic velocity dispersion because there'd be collisions between the molecules. They're point masses, just like molecules are points, but they never collide with each other. See that purple thing there? That's a sort of a reasonable projection of a line of constant density stars, and you'll notice that it's quite flat. So this looks a bit like a oblate spheroid, but it's not. If I rotated it around the minor axis, I got a flying saucer with 2 long axes, 1 short axis. But I could have rotated my ellipse around the long axis. That would be called a prolate spheroid, which has the shape not of a flying saucer, but the shape of a cigar. It has 2 short axes, which are identical because it's been rotated, and 1 long axis. Now everything's on the table here. Maybe by accident, they're oblate spheroids like flying saucers, but maybe some of them are more cigar-shaped. Just to really blow your mind here, maybe some of them cannot be formed by the rotation of any ellipse. They don't have that much rotational symmetry. They look like this picture here, which is the infamous triaxial distribution. It has 3 different axes. Short axis here, which is the vertical axis. There's a very long axis this way. And then there's an intermediate axis here, which is somewhere in between the short one and the long one. This darn thing looks like an ellipse from pretty much any way you look at it. There is evidence that requires that many elliptical galaxies do have some triaxiality to them. The good news is they're fairly close to being oblate spheroid. The reason I say that is because there are 2 long axes, and they're pretty darn close to each other. The shorter axis is only maybe 5 or 10% less than the long axis. For example, many elliptical galaxies, here's what they look like in space. This is a triaxial distribution. So there's the long axis, there's a short axis. You have to think about your viewing angle. The eyeball is looking at them from this direction here. If you look at this, elongated this way, but if you look at one in the center, it actually seems to be tilted the other way. The isophotes that you would observe, as viewed by this just random observer, the isophotes have a different major axis from the inside of the galaxy to the outside of the galaxy. And that can never happen with a prolate or an oblate spheroid. It requires a triaxial galaxy to explain a fairly well-known thing in elliptical galaxies, that they sometimes have these isophote twists. There's not just one value and one position angle for all the ellipses with one constant b over a value. So that's one proof that, sorry, galaxies are a bit more complicated. Oh, they're close to an oblate spheroid, but they're a bit more complicated.